microphone will record. I'm just gonna put it right there. Okay, so yeah, thank you guys for being here. Good morning. Welcome to Defense 1 of 6, or maybe welcome to the 2019 Suncat Summer School. I don't know. We get a little sneak preview. Yeah, so thank you for being here. This is us. This is the world. This is the Earth. Up there, that's the sun. The sun is very gracious. The sun supplies us with an incredible amount of power, an incredible amount of energy to the tune of hundreds of petawatts, more energy than we could ever conceivably use. And we're getting much better at harvesting this energy using photovoltaics. But even though we're getting better at that, we still don't have the ability to control when the sun rises and sets. So while some of us are tanning on the beaches in Hawaii here, others of us are sitting in darkness on the East Coast. And they still have their lights on, they still have electricity thanks to fossil fuels, but that's obviously not the most sustainable route. And it would be nice if we could harvest some of this excess energy during the day and then use it during the night when we need it. And one route of doing this is to store that electricity in the form of chemical bonds. So this is a sort of an essential step, energy storage, to transition away from fossil fuels. So the way that we do this, essentially what I'm saying is that we can convert a low value chemical with excess electricity into a high value chemical. So for instance, we can take water, convert it into oxygen and hydrogen gas. Hydrogen is a very important chemical feedstock, and also the most, on a per mass basis, a very dense chemical fuel. And then when we need electricity, we run this reaction in reverse, and we get electricity out. Now this talk is going to focus more on the chemical production side of things. So we're going to be producing hydrogen from water, and we're going to talk about how to make this process as optimized as possible. So the process might take place in an electrochemical cell that looks something like this. And if we think about all the things that need to happen for this reaction to run, we've got these two electrodes submerged in this electrolyte. They're connected through some external circuit. First, the water has to diffuse to the anode surface, where it then undergoes surface reactions to create protons, electrons, and oxygen gas. Those reactants diffuse away, or those products diffuse away. The electron travels through the external circuit, increasing its potential energy along the way. And then it's reunited with protons at the cathode, where it's now very reactive, and it can form hydrogen gas, which diffuses away. So all of these steps have to happen efficiently if we want to have an energy efficient process. And specifically, what we're going to focus on is the surface reaction part of things. So namely, this is what's referred to as the oxygen evolution reaction and the hydrogen evolution reaction. So how can we sort of facilitate these reactions as efficiently as possible? And thankfully, we can actually think about these two completely separately from one another. Even though they run together in the electrochemical cell, we can think about optimizing them independently. And towards that goal, I want to gain a little bit of intuition for just a one electrode picture. So for instance, let's talk about hydrogen evolution, the hydrogen evolution reaction, where we're turning protons and electrons into hydrogen gas. So the goal is to take these protons in the electrolyte, these electrons in the electrode, and turn it into H2. And we might ask the question, how do we run this process? How do we drive this process? So this is what you do. You go in the lab, you take your little potentiostat knob, and you crank it down to lower potentials. I think that's exactly how it works in the lab, I'm pretty sure. And what this does is it actually floods the electrode with electrons. We shuttle electrons into the electrode to maintain charge neutrality. We'll also end up with some counter charge in the electrolyte that will be attracted to the surface. And what this forms is the electrochemical double layer. And this is at the heart of electrochemistry. This is what drives electrochemical processes. Really what it does is it sets up this potential drop, or this potential change across the interface, which effectively makes the electrons much less stable in the electrode. It makes them want to be on the other side of this potential drop. So what this does is it facilitates the reaction, drives the reaction towards making H2. So let's say this is like a 1 volt potential drop. To achieve that, we basically have to put in about 1 electron per 10 surface atoms, which is not very much. And you know, this is not the only way to drive the reaction. Of course, we could also drive the reaction by just flooding, just adding protons to the electrolyte. Right? Just based on Le Chatelier's principle, if we add protons will drive the reaction to the products. If we wanted to achieve the same driving force that we get from this 1 volt potential drop, that would require about 17 units of pH. That's 17 orders of magnitude in hydrogen proton concentration. So right away we can see the power of electrochemistry. So this is kind of like a zoomed in view. If we take a sort of a macroscopic view, this is what an experiment might look like. So where we're looking at the electrode potential versus RHE. So when we're at 0 volts versus RHE, this is when we're at equilibrium. We're not making any hydrogen. And we might be interested in the current density, or this is really the rate of the hydrogen that's being evolved. And so, like we said, we crank the potential down to lower potentials, and then we see this current, this exponential behavior here that onsets. But we had to put a lot of extra potential beyond the equilibrium potential to get that current out, to get these rates, and that's what's referred to as the overpotential. And this directly contributes losses to the process, energetic losses. If we wanted to get rid of this overpotential, we can use what's called an electrocatalyst, which might give us a profile that looks something more like this with a smaller overpotential. So what electrocatalysts do is increase the rate of the reaction, reduce the overpotential, and thus improve the energy efficiency of the process. And the focus of this defense, of this thesis, and our work at SunCat is to use theoretical simulations to simulate these processes, which allows us to rapidly screen various catalysts and also gain atomic level insight into catalyst behavior. What makes a good catalyst good? So speaking of which, what makes a good HER catalyst? How do we actually facilitate this using a catalyst? So we talked about how we drive this total reaction by decreasing the potential of the electrode, but where does the catalyst come in? So this is sort of the initial state, and this is kind of the end final state product, but we have some intermediate state, which is one of these protons adsorbed on the surface. And we could imagine plotting out the free energy diagram for this process where we have hydrogen adsorbed. And if the catalyst is strong binding, then hydrogen is going to be favorable. It's going to be downhill to bind hydrogen. This is not so great from a efficiency point of view because we essentially have to go uphill to get the hydrogen off the surface. And this is what's referred to as the theoretical overpotential. This constitutes a loss in the energetic efficiency. If we have a weak binding catalyst, then it's uphill to get hydrogen on the surface. And if we have something that is essentially thermoneutral, where hydrogen binds without any driving force, that's sort of the optimal case. So we can think about sort of finding the surface with the optimal hydrogen affinity. Ruthenium reactivity is too high, gold is too low, and platinum is sort of just right. And platinum is well known as the best HER catalyst. So to use calculations to evaluate electrocatalysts for HER just comes down to calculating this energy difference, essentially the energy associated with absorbing a proton. So how do we do that? Well, we use a tool called density functional theory, and I will talk about it a little bit more in a few slides, but for now, let's just say that it's essentially a computational technique that takes in atomic positions and most importantly gives us the energy of the system. So it's an atomistic simulation, so we actually have to now think about actual atoms instead of just this continuum electrolyte and electrode. So our simulation might look something like this, where we're going to take this proton and eventually it's going to end up on the surface. And we'll calculate the energy difference between these. Now this calculation would be extremely difficult to do. For one, there's a lot of atoms, a lot of electrons. This is very expensive to do, but also there's a lot of degrees of freedom in this bulk electrolyte. There's a lot of sampling that would have to be done to get a good view of this system. So we'd like to just get rid of that bulk electrolyte. The problem is that's where our reactant proton sits. So to deal with this, we use a little computational trick. Namely, we recognize there's that we can write out the delta G for the HER, or half of HER, and that's just equal to the electrode potential on an RHE scale. And the delta G is just the difference between the electrochemical potentials of these species. So we can actually write out the electrochemical potential of the proton and the electron in terms of just hydrogen gas at standard conditions and then this potential term. So what we effectively do is replace that proton with H2 gas. And we do a separate calculation with H2 gas, and we essentially can correct for potential using this term, and this is known as the computational hydrogen electrode. We can make two additional simplifying assumptions. For one, we still have this double layer intact. This double layer essentially has a field that it creates. And if we're talking about something like hydrogen, it probably doesn't interact with this field very much. It doesn't have a large dipole moment. So maybe we can just ignore the charge at the interface. And we could go even further and say that maybe this adsorbate doesn't really interact with the solvent directly. Maybe we can just get rid of the solvent altogether. And this is like the simplest electrochemical calculation that one can do, where it essentially looks like we're doing thermal catalysis now. And all of the electrochemistry is really just wrapped up in this potential term. So this is like a very, very powerful and tractable way to evaluate electrocatalysts with DFT. So I mentioned I would say a little bit more about what DFT is, and let me do that right now. As I said, it's an atomistic model. And so we essentially are solving the Schrodinger equation for the electronic and nuclear degrees of freedom. Thanks to the Born-Oppenheimer approximation, the fact that electrons are much lighter than nuclei, we can split this into two separate Schrodinger equations, one of them over the electronic degrees of freedom and one of them over the nuclear degrees of freedom. DFT essentially recognizes that this many-body wave function is very difficult to deal with when you're working with more than 10 electrons or so. So instead, we reformulate everything in terms of the electron density, and essentially we're just minimizing, we're trying to find the electron density that minimizes the total system energy. So we essentially assume nuclear positions, the nuclei are fixed, and we ask, what is the electron density that minimizes the energy? So there's some optimization here where we figure out the right electron density. And we repeat this process for various distances d, and we map out the energy at different proton-proton distances. So this is essentially simulating a hydrogen molecule. This gives us what's known as a potential energy surface, and this potential energy surface is then directly plugged into the nuclear Schrodinger equation. This is the potential energy for that equation, and we know that we have a Schrodinger equation near the, at least if we do a Taylor expansion around the minimum of this well, it's roughly quadratic. We can Taylor expand it to second order, and if we have a quadratic potential and a Schrodinger equation, we know how to solve that. It's just a quantum harmonic oscillator, and we can get our enthalpies, entropies, free energies as a function of temperature. So that's how it works, and compared to experiment, it works quite well. Using the exchange correlation functionals that we're going to be working with in this talk, we get mean absolute errors on the order of about 20 kilojoules per mole, or 0.2 electron volts. So that's DFT in a nutshell. And that's kind of a broad overview of electrochemistry as well. This talk is going to focus on the oxygen evolution reaction specifically. So we were talking about HER before, now we're going to talk about OER. And let me just give a very brief overview of how we think about OER theoretically. We need to come up with a mechanism in the same way that we came up with a mechanism for HER, and that mechanism might look like this, where we start with two water molecules. We have a catalyst surface. We adsorb one of the water molecules and deprotonate to make OH, deprotonate again to make O. Attack with the second water molecule to form the OO bond and simultaneously deprotonate to form OOH, and then desorb as oxygen gas, releasing 4 protons and electrons along the way. And we can also map out the free energy diagram for this process. And once again, we can identify the most difficult step. In this case, it's this OH to O, and that is our theoretical overpotential, which contributes losses to the system. Now, it turns out if we change the catalyst material, we can't. Like these energy levels do not change independently of one another. They're very much correlated to one another through linear scaling relationships. And it turns out that once you take those constraints into account, the two steps that are almost always limiting are either this step, OH to O, or this step, O to OOH. So we can actually think about this as essentially trying to find the correct oxygen reactivity. Right? If our oxygen is too reactive, then it doesn't want to let go of this hydrogen. So we get stuck on OH to O, which is the case that we're looking at. And if oxygen is not reactive enough, it doesn't want to form the OO bond. So that would be a low reactivity oxygen. And so, yeah, we can think about OER as finding the optimal oxygen reactivity. And that's an important thing to emphasize to understand the rest of my talk. And a metric that we can use to measure the oxygen reactivity is the difference in energy between O, adsorbed O, and adsorbed OH, which is basically this energy difference here. So we can use those scaling relations that I mentioned to construct a volcano as a function of this oxygen reactivity, where we see that there's an optimum at an intermediate oxygen reactivity. And we can overlay experimental data. For these data points, the Y values are now the overpotentials required to reach some current density, 1 milliamp per centimeter squared. And the X values are the theoretically calculated oxygen reactivities. And we see that they roughly follow this volcano relationship quite nicely. So it seems that this relatively simple model works reasonably well. Okay, so that's the introduction. I have 3 stories that I want to talk through today. And the first one is about ruthenium oxide defects. And we're going to essentially start this story right where we left off with this volcano. So you'll notice that ruthenium oxide 110 does not fall on this volcano. Experimentally, it's quite active. On the y-axis, it's about as active as anything else. And on the x-axis, this is the theoretically calculated oxygen reactivity. It's very, very reactive. It's too reactive. We would expect it to not be a good catalyst experimentally, but we know that it is. So we have this question: why doesn't our model predict ruthenium oxide to be highly active? Towards answering this question, I want to discuss the metastability of the ruthenium oxide surface. So here I have a series of cyclic voltammograms for ruthenium or ruthenium oxide in acidic electrolyte. And if we follow this cyclic voltammogram, if we follow this first one here, it goes up, it comes down, there's not really anything happening. Now if we go a little bit higher, eventually oxygen evolution onsets, so now we're running OER. And when we sweep back down, we see this very interesting reduction peak. And the authors have evidence that this reduction peak is actually reducing RuO4, dissolved RuO4 into ruthenium oxide. So presumably this RuO4 is being created during OER, the surface is dissolving, and then being redeposited when we sweep back to reducing potential. There's further evidence of this dissolution in a more recent study, where in black we're essentially showing the potential required to reach 30 milliamps per centimeter squared, which is pretty constant. So from an activity point of view, the activity is very constant as a function of time. But using a quartz crystal microbalance, we can measure the mass of the electrode and see that it's steadily decreasing. So this also suggests that the surface is dissolving while the reaction runs. So this is like an STM image of a 110 single crystal of ruthenium oxide. This is kind of how we might think about sort of a very pristine ruthenium oxide surface. And we might model it in DFT, looking like this, with where we have what are called cuss rows and bridge rows. And it's important now to keep in mind that, based on the previous slide, the surface is metastable, and maybe we should be considering a surface that looks something more like this. So the question becomes, how do we model a sort of defect surface like this? And we ask the question, could defects that form during dissolution actually be responsible for the OER activity? So let's try to answer that question. I just want to run through some different active sites here. This is that 110 ideal terrace without any defects at all. Here we have calculated the oxygen reactivity for this cuss oxygen. This is generally what people would assume to be the active site for OER. It has an oxygen reactivity of 0.9. You can see that's why we're so far left on the volcano here. This is a very unreactive oxygen. If we just make a single defect, if we just remove a ruthenium atom from the bridge row, we open up a new singly coordinated oxygen here, which is actually much more reactive with the reactivity of 1.2 electron volts. So we're sort of moving right on the volcano. We can look at some other defects. So we have these steps that you can see in the STM. This is an example of a bridge terminated step. We can look at the reactivity of these oxygens. They're actually not very reactive. We can also look at a cuss terminated step, not very reactive. And finally, we can also look at kinks. So kinks are essentially the point where two steps meet one another. So here we have a cuss step, and then behind it, it terminates, and then we have a bridge step. So right here is what we'd call a kink. And we can have 4 different types of kinks for this material, and I'll just show in detail one of them, specifically this what I'm calling a double kink. It looks something like this. So you can see the cuss step extends, and then it terminates, and then right behind it we have this bridge step. It terminates immediately, and then we have a Cuss step again. And there's lots of different singly coordinated oxygens at this surface. Most of them, well, all of them are more active than the ideal 110 oxygen, with the most active one sitting right there at the cake. So we can summarize all this data. We can plot the oxygen reactivities for all these different sites, and we can see compared to the 110 ideal facet, we have many that are much more reactive and much more active for the oxygen evolution reaction. So if we consider this sort of spread in active sites that seem to exist based on our calculations, now there seems to be a little bit more agreement with experiment. We have some oxygen reactivities that are sort of in line with the experimental observations. So I think that from this work, we hypothesize that these defects that are formed in situ may be responsible for the well-known activity of ruthenium oxide. And I think that this is just a really nice example of one of the great challenges in studying electrocatalysts with DFT is choosing an active site. And it's especially difficult when you're studying a material that is known to be metastable, that is known to be dissolving under reaction conditions, because it creates a whole variety of sites that one may study. Okay, that's story number one. I want to now move on to story number two, and we're going to pick up right where we left off. So something interesting about this work is that we found this very wide range of reactivities in oxygen. And these are all oxygens at a ruthenium oxide surface. So we kind of would like to dig a little bit deeper into why this wide range exists. So it's known, there are many examples in the literature of correlating atomic structure with reactivity. So this is sort of an analogous case where we're looking at various platinum nanoparticles and platinum surfaces and looking at the binding energy on those different, at those different platinum active sites. And what we see is that the binding energy of OH or OOH scales very well with sort of the coordination number of the platinum atom to which it's binding. This generalized coordination number essentially is just the coordination number of the active site, and then also taking into account the coordination number of the atoms to which the active site is bonding to. This doesn't really apply so well to our case, looking at ruthenium oxide. If we consider this oxygen atom, it has a single coordination to ruthenium, and the ruthenium is always octahedrally coordinated, so it always has six. It always has a coordination number of 6. So the generalized coordination number for all of the sites that we've been looking at is the same. That we can't really use atomic structure to rationalize these differences in reactivity in our case. So we have to turn to electronic structure. And electronic structure, of course, is what governs chemical bonding. So it makes sense that correlates with surface reactivity. And I just want to give an example of how that works. So here we've got, we're going to look at two cases, ruthenium and gold. And we're looking at the density of states of a surface atom, specifically the density of states projected onto D states. So if you're not familiar with density of states, you can just think of this like orbitals. Like we're just looking at orbitals as a function of energy, and we fill the lowest lying states, and then right at the Fermi level and above, we stop filling states. So ruthenium only has 7 d electrons, so it has some unfilled d states, whereas gold has all 10 d electrons. It has completely filled d states. And we can think about what happens when we couple those d states to oxygen 2p states. And there's some broadening here because we've allowed the oxygen to couple to some of the S and p states of the metal, but don't worry about that too much. But we can think about what happens when we couple these states to the metal d states. We form, just like in molecular chemistry, we form bonding states at low energies and antibonding states at high energies. And we can see in both cases, the bonding states are completely filled. But in the case of ruthenium, the antibonding states are only partially filled, whereas in the case of gold, the antibonding states are mostly unfilled, or sorry, mostly filled. So what that means is that gold binds oxygen much weaker. And the reason that these antibonding states are mostly filled is because the D states of the metal are so much lower than the D states of ruthenium. So there's this very nice correlation between the position of the D states and the reactivity of the surface, namely that if you have higher D states, you have a more reactive metal. And this is the very well-known D-band model. So we wonder, can we apply this type of thinking to oxygen reactivity? Here I'm showing one of the kinked surface that I showed before, where there's a bunch of different oxygens. I'm showing the reactivity of 3 of them, and we can calculate the density of states projected onto those 3 oxygens. And we can see that they have some similarities. There's some subtle differences. But we can just, inspired by the D-band model, we can just compute the average of this distribution, which is represented by the dotted line, and do that for all of the calculations, all of the different oxygens that we looked at in this study, and we find a pretty strong correlation. So that's nice. We found something, some fingerprint, some electronic structure fingerprint in this case that correlates with oxygen reactivity. And naturally, we wondered, does this extend to other materials? In fact, it does. It actually appears to be a pretty robust correlation. So again, we're plotting oxygen reactivity versus this average 2p state energy of the oxygen. And we can see a reasonably strong correlation consisting of FCC metals, rutile oxides, perovskites. And what we see is that if you have higher 2p states, you have a more reactive oxygen. This is really neat. I mean, this is like almost like a direct analogy to the D-band model that we talked about, where in the case of transition metals, when you have higher D states, that corresponds to a more reactive metal. And what we're saying in this work is that higher P states correspond to a more reactive oxygen. Another point that I want to emphasize is that there's a sort of structure sensitivity to this correlation. So not only are we changing, going from gold to ruthenium to titanium, platinum, we're also changing the active site, or the site where the oxygen sits. So in the diamonds, it's doubly coordinated. In the triangles, it's threefold coordinated. And in the circles, it's on top. And those still move you up and down this correlation. So there's some sensitivity to both the composition and also the site where the oxygen sits. And we can just use like a toy system to kind of explore this a little bit more systematically. So along one axis, we can vary the reactivity of the metal. So we can go from titanium to gold. And along the other axis, we can vary the coupling between the metal and the oxygen. So this is sort of like changing the active site. And we can compute the oxygen reactivity at these various bond lengths on various metals and plot the results on a grid. And there's a lot of information here, but really the only thing that I want to show that I think is kind of interesting is if we take a look along the diagonal here, all of these cases have almost the same oxygen reactivity. So if we look at oxygen far away from titanium or oxygen pretty close by to gold, those oxygens have roughly the same reactivity. But that's kind of surprising because if you look at their electronic spectra, if you look at the colored spectra and those diagonal elements, they look like wildly different, I would argue. But it turns out that just taking the average of those spectra serves as a very good summary statistic of the oxygen reactivity, in the sense that all of these diagonals also have almost exactly the same average 2p state energy. So it seems that this average of the spectra is like an excellent summary statistic for describing oxygen reactivity. That's a little bit of a digression. I do want to stay a little bit on the practical side of things and talk about some of the practical benefits of this correlation. For one, it gives us predictive power. So what it allows us to do is take a very complicated surface like this ruthenium oxide kink and actually calculate the average 2p state energy of every oxygen on the surface, of which there are more than 30, and they're colored by their average 2p state energy. And then from that, we can directly predict the reactivity of those oxygen atoms. So we see that those variations in the 2p state energy directly correlate to variations in oxygen reactivity. So when we're looking at sort of big nanoparticles with lots of unique active sites where it's quite difficult to probe all of them individually, we can actually get an estimate of the reactivities from a single calculation of a single DFT calculation, as we've done here. Okay, the third and final part of the presentation, we will be talking about transition states and kinetics. So, this is the picture we looked at in the introduction. As I mentioned, the metric that we use for our activity is this theoretical overpotential. which is essentially the height of the largest step on the free energy diagram. We use this to construct a volcano versus the oxygen reactivity. But there's something really important to point out here, and that's that this theoretical overpotential is, at the end of the day, like a theoretical construct. It doesn't necessarily correspond to anything observable experimentally. So if we want to get closer to what is being observed experimentally, we really need to be calculating rates, calculating current densities at different potentials. And to do that, we need kinetics. So that's what we're going to try and do in this section. So to do that, we're going to sort of consider a slightly expanded OER mechanism where now we have all elementary steps. Elementary steps are important when you're considering kinetics. First, this time we'll just adsorb water before it's deprotonated and then deprotonated separately. Continue as normal through OOH, and then we deprotonate OOH before it desorbs as O2. And the goal now is to compute barriers for all of these different steps. We'll begin by calculating the barrier for our favorite reaction here, OH to O. And I have an image of what the transition state for that reaction looks like as found using DFT. So we can see we begin with this OH adsorbed on this Cuss site, and then it's transferring its proton to a water molecule in the water layer. And you can see it's nicely shared between them in the transition state. And if we take a look at the reaction coordinate, we see that the barrier is very small. This is 0.05, less than 0.05 electron volts. This is almost like kBt is the height of the barrier. So this happens almost instantaneously, which is good to know. And what it allows us to do, what we'll just assume is that there's no additional barrier for this process. And maybe it's not surprising that there's no additional barrier, because after all, we're essentially just taking this proton from one electronegative oxygen to another over a very short distance. And furthermore, we'll assume that similar deprotonation steps are also easy, such as water deprotonation and OOH deprotonation. And this leaves only a single electrochemical step remaining, which is O to OOH. So this one is a little bit different in the sense that we have to actually form the OO bond. Now, before we do that, I just want to give a very brief explanation of electrochemical barriers and some of the difficulties in calculating electrochemical barriers. So ultimately, what we'd like to calculate is the barrier as a function of potential. We'd like, hopefully this should be a linear relationship. So the way that we'd set up a calculation like this is we have our initial state, which with oxygen on the surface, and we have some water layer. We have a transition state where the OO bond starts to form. We also start to transfer this proton to a neighboring water molecule. And then in the end, we end up with OOH on the surface and a proton in the water layer. For the purposes of calculating the barrier, it's just the difference between these two energies, so let's not worry about the final state right now. So we can do this. We can get a barrier. We can calculate an EA for this process. But something, a sort of a caveat or a subtlety that you have to keep in mind is that when we do DFT calculations, we usually have periodic boundary conditions. So the simulation we're actually doing looks something like this. And if we take a look at the transition state, we sort of have a partially charged double layer. Right? We have some partial negative charges and partial positive charges. So we have a double layer that's been charged in the transition state that doesn't exist in the initial state. So essentially, we're simulating two different potentials here. In the initial state, we're at a high potential, and at the transition state, we're at some lower potential, and the final state, we're at an even lower potential. So we do this calculation, we get a barrier, we get some activation energy, but we have two different potentials. So we sort of get like a smudge on this plot instead of a single point, which is what we would like. We can make this smudge smaller by doubling the size of the cell, such that when we go to the transition state, we have half the density of partial positive and partial negative charges. This is expensive, but we can do it. So we can double the cell, and the smudge will decrease by roughly a factor of 2. We could quadruple the cell, it'll decrease again, so on and so forth. If we go to an infinitely sized cell, eventually these will collapse down to points. But of course, that's intractable to do with DFT. So yeah, and we're going to make an assumption here that is actually a pretty reasonable assumption, and I won't go into the details of it right now, but essentially it relates to the electrostatic interactions between the double layer species and the transition state. And if we assume that those are sort of mean field interactions, they're linear interactions and they're proportional to the size of the dipole moments of the species involved, then what we can do is actually collapse these smudges down to the midpoint and actually end up with points on this plot, which is what we want at the end of the day. And that's exactly what we've done here for O to OOH on iridium oxide. We have 3 different cell sizes with the barrier calculated effectively at 3 different potentials. Another way that you can change potential is by modifying surface coverage. That's a perfectly valid way of changing the electrode potential, and that's essentially what these points are here. So this is adding protons to the surface, and this changes the potential. And the fact that these all fall on a line kind of tells us that these assumptions that we made about the electrostatic interactions between the double layer species also applies to the electrostatic interactions with the adsorbates on the surface. But ultimately, we get out this nice barrier as a function of potential, which is what we want. Here is an image of the transition state. We can see the OO bond starting to form. We can see the proton transferring to a neighboring water molecule. Oh, and by the way, these barriers are quite big, right? So at OER conditions, somewhere around 1.5, we have barriers that are of the order 0.7 eV. So these are not negligible. We need to consider these barriers. We'll draw a barrier there. There's only 2 steps remaining. Water adsorption. Water binds quite strongly to oxide surfaces. We're in an aqueous environment. We don't really have to worry about diffusion, so we'll just assume that this is quite easy. O2 desorption is a little bit tricky to actually calculate a barrier with DFT because of the entropy of the transition state. Based on experiments, though, using like temperature programmed desorption, it appears that O2, at least on a ruthenium oxide surface, is able to desorb at 150 Kelvin. So based on that, we assume that at 300 Kelvin, there's really no issue getting O2 off the surface. So basically what we're going to do is just assume that this one step here with the barrier, OOH formation, is the sole rate determining step for the process. Now if we want to go and make a volcano relationship, we need a scaling. So this is a scaling relationship for our barrier as a function of the oxygen reactivity and the electrode potential, because it's an electrochemical step. So we can plot barriers calculated on different materials as a function of the oxygen reactivity and the electrode potential, fit essentially a 2D plane to that data. That gives us our scaling relationship, and you can see that based on this parity plot, it fits quite well. Okay, so let's talk about kinetics now. If we assume that OOH formation is the rate determining step, then we have a very simple expression for our rate. It's just the coverage of oxygen times the rate constant for OOH formation. And so we can take a look at a free energy diagram, a simplified free energy diagram where at low potentials, OH is more stable than oxygen. So the effective barrier is essentially going from OH to the transition state. And as we go to higher potentials, oxygen will eventually become more stable than OH, and now we're only limited by the barrier for OOH formation. We're effectively just limited by this rate constant. And if we take a look at a Tafel plot from this model, so we're looking potential versus log of current density, we see that there is a sort of a transition here where at low potentials, we're OH covered, we have a low Tafel slope, and then at higher potentials, we're oxygen covered, we have a higher Tafel slope. We have this kink that occurs. And so this is for an oxygen reactivity of 1.7. We could look at a different oxygen reactivity of say 1.4 EVs, and the kink happens somewhere else. And this type of kink behavior is actually something like what is observed experimentally. So here's ruthenium oxide 110. You can see the 2 different Tafel regimes there. Finally, we can make a kinetic volcano. So here we're going to plot the potential required to reach various current densities as a function of the oxygen reactivity. And interestingly, shown in red here is the thermodynamic volcano that we showed originally. This is based purely on the thermodynamics. It actually, the position of the peak, it agrees quite well with the 1 milliamp per centimeter squared volcano. It's kind of an interesting result. Although the legs, the slope of the legs are quite different. And another thing to notice is that the horizontal position of the peak shifts depending on what current density you're interested in. So in other words, the optimal catalyst is slightly different depending on how quickly you're trying to run the reaction. We can also think about how this scaling relationship is limiting us. So here I'm just showing the potential required to reach 1 milliamp per centimeter squared as a function of the barrier height, so the transition state relative to oxygen, and the oxygen reactivity, or the negative of the oxygen reactivity. And we can see this is the transition state scaling. And if we want to get catalysts that are significantly better than what we currently have, if we want to get away from this 0.3 volt overpotential, we essentially want to get down in this region. What we need to do is stabilize the transition state relative to OH. In other words, we need to make oxygen more interested in this OO bond formation transition state without affecting its affinity towards hydrogen. I think this is a very, very difficult task, and I think it makes a lot of sense why we haven't really found anything in this quadrant to date. Okay, the last thing I just want to show, I just want to kind of tie it back to experiment a little bit. I've compiled some experimental TAFL data here. So we can see, this is all from experiment, we can see some of these kinks that occur for different materials. Now, the interesting thing about the model is that this kink occurs when OH and O are at the same energy. And OH and O are at the same energy when the electrode potential is equal to the oxygen reactivity, or the descriptor value. So in other words, from the kink, we can determine that the oxygen reactivity, or we can estimate that the oxygen reactivity is equal to the kink potential. So in this case, maybe it's 1.67. In this case, maybe it's 1.85. So what we can actually do then is plot this experimental data on a volcano where the x-axis is actually the experimental kink potential. So on the x-axis, we have the experimental kink potential, and on the y-axis, we have the experimental potential required to reach 1 milliamp per centimeter squared. So these points are purely derived from experiment. And then we have this volcano, which is the same one I showed before based on our calculation. We can see there's a lot of clustering of points here near the peak of the volcano. These are the most often studied materials, likely because they are the most active. But it's interesting to consider some of the less active ones, specifically platinum. You can see platinum has a kink at very low potentials, and meaning that it suggests that it has a very unreactive oxygen. And it's also one of the worst OER catalysts on this plot. So that kind of makes sense. We can look at the opposite case, which is gold. Gold, we have measurements all the way up at 2 volts, but it still has a low TAFL slope. So we infer that it hasn't kinked yet, and maybe if we measured higher, it would kink eventually. So we infer that the descriptor value is something higher than, say 2 or 2.1 volts, which is represented by this right-facing arrow here. So it has a very, very reactive oxygen, and it's the worst OER catalyst on this plot. So I think that there's some insights that we can gain about the experimental activity. Okay, wow, we did it. That's all 3 of the projects that I wanted to go through. Thank you guys for your attention and for listening. Wow. We're all getting very sleepy.